This is kind of a project. I worked on a number of former aluminum smelters over the last decade or so, and it was interesting to me as a geochemist that the geochemistry of fluoride had not perhaps been factored into the level I would have expected, given that it's not overly complex, but it's very interesting because it takes on many facets. Uh, the reason we have a number of aluminum smelters, some are still operating, but most are former, in the Northwest, is because at the beginning of, say, in the pre-World War II era, Reynolds Metals Company, Reynolds Metals, they were actually Reynolds Tobacco Company, decided they needed to make aluminum foil uh, for their cigarette packages, for packaging. And they had built a number of facilities across the country, some in Tennessee, uh, where the ore deposits were located. Eventually, also in the Northwest, and there are a number of these sites. But what happened right around at the start of World War II, there was a big push to build airplanes, and so the aluminum industry actually took off. It went from making aluminum foil for cigarette packaging to building airplanes and so forth. Boeing in Seattle, for example, was a big consumer of the products. And then following World War II, the production of consumer goods made out of aluminum and so forth kept that industry going for a long time um, until recycling became important. And then the primary production of aluminum from ores was kind of a smaller and smaller portion of the total production. And so many of these facilities have, they're often waterfront industrial facilities, so, high value real estate. But they do have a legacy of all this past industrial activity. And one of the things that kind of often crops up is residual fluoride. Uh, and that's why I'll be talking about that. I should mention just some acknowledgments. Some of my coworkers that have been working on these sites with me, Masa Kanematsu, who manages the laboratory in Portland, Minakari, who's one of our groundwater modelers. Rebecca Gardner is an engineer who signs off on all of the designs for the remedies and so forth. And there are project managers, Kendra and Nicole. Most of these folks are in Portland, except Rebecca, who's in Seattle, actually. And so, as I said, this particular aluminum smelter on the Columbia River it's basically in Longview, operated from the early 40s to about 2000, and the legacy of impacts there include soils and solid media from residues from the production that contain up to a few percent of fluoride, as well as groundwater that's been contaminated with a few hundred, well, a couple thousand, up to a couple thousand milligrams per liter of fluoride. Just for reference, the maximum contaminant level for drinking water, which is often what applies for groundwater cleanup, is 4 milligrams per liter. So few orders of magnitude above that. How did the fluoride get there? I'll talk a little bit about the aluminum production process and why fluoride is such an important component of it. One of the processes that was used more widely, it was called the Hall-Héroult process, which involves taking aluminum oxide concentrates from the ores and placing them in a carbon-lined pot along with a flux. This flux was typically cryolite, which is a sodium aluminum fluoride, and then applying current so that everything gets really hot and the aluminum oxide starts to melt. The flux reduces its melting temperature, and so that was really important to keep the process more energy efficient, cost efficient. And because it's in contact with carbon, with a reduced component, the aluminum oxide components actually become reduced to aluminum metal. And that's how they would make the molten aluminum metal. It would be poured off and shaped and so forth. The cryolite was a key component of the process. And because it's not really available naturally in kind of it's not a widespread common mineral, it's relatively rare. One of the things that they did do is try to recover the spent cryolite from or from the actual pot liners, the carbon liners. So they would crush up these carbon liners once they were no longer usable and try to leach out these fluoride salts and reprecipitate them so that they can be reused. And a lot of the process residuals, which still had some residual fluoride in them, were managed on site in landfills. And so we have these sources of fluoride on site. And kind of just to give you a picture of where the stuff ended up being located, you can see here, I don't know if, can you see my mouse on the screen?
Yes, we can.
Okay, perfect. So this is the part of the site. So here's where all the facilities were and the lines, the pot lines, essentially. This area here in blue is where the cryolite recovery took place. And then these various, these two landfills were where some of the residuals would be stored. There's some other places where, after 60 or so years of operation, you run out of space, you start looking for other places to put some of the stuff. There are some materials here that also contained other residues and debris here as well. And then from the early portion of the operation of the site, there was a RECRA facility. It was closed as a RECRA facility. This was a landfill where this was prior to cryolite recycling or recovery. And so this was material that probably contained higher concentrations, but it's not marked here because you can't sample this because it's essentially a closed landfill. But the soil surrounding it, you can see all green, means that they're below the screening levels for fluoride. So we identified the potential source areas for groundwater impacts. And looking at groundwater flow directions, you'll see this better probably on the next slide, but essentially the site is surrounded by a system of ditches that are maintained at a level below the Columbia River in order to prevent flooding. It's on river floodplain, and so you don't want a facility that was operating high voltage processes to have the risk of flooding. That could be disastrous. And so that's been there forever, and it actually is a very strong control on groundwater flow directions at the site. And so on the west portion of the site here, where this closed RECRA facility and other landfills are, groundwater generally flows from the river towards the ditches and tends to take a arcuate path in this direction. On the eastern side of the site, where the recovery processes took place, from the uplands part of the site, groundwater flows towards the ditches again, but there is a divide here. There's actually a dike that runs along the river's edge, another kind of flood protection measure that was installed. So a portion of the groundwater flows towards the river, but most of it beneath the historical operations flows towards the ditch up inland. And so when we sampled groundwater, what we found was sort of this kind of pattern where really the elevated fluoride, which would be sample locations marked in yellow or blue, and also areas highlighted in those colors because they tend to be associated with the footprint of the source material, and purple, which is very high, which is the highest concentration. This is right in the cryolite recovery area. It's also associated with very high pH, greater than 9, typically up to about 11. And that's because sodium hydroxide was used to leach the fluoride out of the spent pot liners. What we see is that, after 60 years or so of this operation and an additional 20 years of monitoring, there aren't really any well-developed plumes that extend far beyond the boundaries of the waste, which was an initial suggestion that probably there may be some natural processes that limit the transport of fluoride in groundwater. And so that was something that we thought was going to be very important to assess. And there were basically two areas of most concern. One was this area next to that closed landfill where groundwater would be discharging to the surface water ditch, and where concentrations in the surface water ditch have kind of bounced around at or slightly above the MCL, which would also be considered the cleanup level here. And then the other area was this high pH, high fluoride area where we've got very high concentrations, but they don't seem to have spread very much, despite the fact that groundwater has been moving towards these ditches for decades. And so that was an area of interest for evaluating the types of natural attenuation processes that may be going on. So I'll start with describing how we developed a geochemical conceptual site model, types of data we collected, and how we developed the understanding of these processes. And then I'll follow with a numerical model that was used to evaluate whether we could rely on these processes, or to what extent could we rely on these processes as helping to maintain protectiveness of surface water quality, which was the ultimate goal for in terms of what the remedy should achieve. It was recognized that groundwater restoration would take a long time, but in the meantime, we wanted to be able to protect surface water quality. And then finally, I'll talk to you about some remedial approaches for a portion of the site where we needed to do something more active than just natural attenuation to achieve those goals. So in terms of the geochemical CSM, we wanted to document the processes controlling fluoride transport. And as I said, assess potential impacts and also evaluate the capacity of the aquifer to be protective of surface water for in the long term. And essentially, I just repeated what I told you. So in terms of the geochemical characterization, we focused on that area and the cryolite recycling portion of the site, collected soil borings, and characterized groundwater, surface water, and pore water in the unsaturated zone. We analyzed total concentrations of fluoride and organic carbon to kind of map out where residues were present versus where soil was present, and identified the minerals in both of those types of materials using X-ray diffraction, high-resolution electron microscopy, as well as various chemical extractions that target different amorphous phases that wouldn't be obvious by X-ray diffraction, just to understand what was there, as well as understanding the cation and anion exchange capacity. And so just to show you a little bit of what we found, this is an electron micrograph image on the right showing a sort of a spherical aggregate of fluoride, calcium fluoride, as well as other clusters and clumps of fluoride crystals that are pointed out there with the arrows. Some clay minerals, you can see these platy substances here, as well as gibbsite. They include both this list of minerals. The soils themselves contain primarily quartz and calcium-rich feldspars, calcic plagioclase, and some montmorillonite clays. And we did find albite, which is kind of unusual in this in this setting here, where we're getting minerals that weather out of the Cascades volcanics. Albite's not particularly common, but it tells us something about the processes that may be going on. I'll talk to you about that in a minute. But the important thing here is, well, this kind of texture that we see here, the spherical fluoride, suggests that it precipitated in place. It's something that precipitated out of water in situ in these soils. And to try to understand, well, what drives that kind of precipitation, we kind of looked at the graph on the left shows dissolved fluoride concentrations in groundwater and unsaturated zone waters, just different color codes there. But what we've plotted on top of that is the red line, which is the calculated solubility of fluorite, the mineral, in equilibrium with calcite, which was also found to be present in many of these soils. And it shows that reaction seems to kind of define the upper limit of fluoride concentrations across a wide range of pH at the site. It's higher at high pH and lower at low pH. But that was an important constraint on fluoride fate transport, and it's supported by the fact that we do find fluoride in the soils. And then, the other part of fluoride is a calcium fluoride mineral. So we know where the fluoride came from. Where does the calcium come from? And as I mentioned, the soils in this area contain calcium-rich feldspars and calcium-rich clays because of the weathering of Cascade volcanic rocks that have come down and deposited on the banks of the river. If we look at a correlation here of exchangeable calcium versus exchangeable sodium, remember sodium hydroxide was used to recover the fluoride in the cryolite recovery process. And in groundwater, high fluoride tends to go with high sodium. And so In soils, we see kind of a reverse here. When we have we don't expect to have very high sodium in the soils because they're calcic rich naturally. But when we see that, we also see a depletion of the calcium, and that suggests an exchange reaction, that it's an ion exchange or either on clays or feldspars or both, but that the soil itself is providing the calcium that reacts with the fluoride to precipitate calcium fluoride and limit the movement of fluoride in groundwater. So that was a major process that needs to be considered in terms of fit transport. There's also evidence for ion exchange on the clay minerals, as I showed you in that electron microscope image. So exchangeable fluoride on the soils. This is an extraction, a cation exchange, anion exchange or cation exchange extraction in the case of sodium. There's a pretty good correlation between the amount of exchangeable sodium, which had to have come from releases from the cryolite recovery area, for example, where you had sodium and fluoride in the groundwater, in the solutions that were in contact with the residues. So there's this correlation which suggests that fluoride was also being taken up by clay minerals and such. And when we look at the relationship between the exchangeable fluoride concentration and the total fluoride concentration in these soils, we see that there's a pretty good correlation at low total fluoride, where likely most of the fluoride has been taken up by on exchange sites. But once you get above a certain level, above about 700 or 800 ppm total fluoride, it deviates from that line, suggesting that this is where these other minerals like fluorite and a few others that I'll mention in a minute actually are where the fluoride ends up in the solid phase. So a couple of different mechanisms: precipitation and sorption by clays and other sites. Another sort of detail here is that because of the high pH in some of these areas, a lot of phosphorus is leached out of the soils. So you can see here, phosphorus versus pH in groundwater. And that phosphorus can be available to react with calcium and fluoride to precipitate various other minerals that we did find. They were rare, but we did find them in the soil mineralogy. These include things like fluorapatite or carbonate fluorapatite, or a very unusual phase of calcium monofluorophosphate. And so that's another secondary precipitation reaction that would affect the fate of fluoride. Now, in terms of how fluoride got into the groundwater to begin with, these process residue deposits that are present either in the fluoride recovery area or in those landfills, we do find that there are fragments of fluoride such as this that don't look like they precipitated, but look rather that they were part of the original material and that have actually are dissolving to provide fluoride to groundwater. And however, the amount of leaching that happens there, you have up to 7% total fluoride in some of these deposits, but the amount of leaching is significantly less. So there's a high, the partition coefficient is quite high in terms of what leaches, or the leachability, and the other side is relatively low. So again, just to summarize, we have evidence, we found evidence for a precipitation of mineral phases such as calcium fluoride, whereby the matrix actually provides the calcium. And so if you think about these plumes, they're surrounded by these calcium-rich soils. That explains why the fluoride hasn't moved very far outside of the footprint of the waste materials, as well as absorption, which is probably more important for regulating fluoride at lower concentrations, as I mentioned. I won't spend too much time on this, but essentially this is just a cartoon that essentially says that along the groundwater flow path, those processes I just described happen, and natural attenuation limits how far a fluoride plume can develop, and is important in protecting surface water quality. And so switching from this, the second phase of this was as part of the feasibility. So this was remedial investigation so far. The feasibility study involved trying to understand, to what extent can we rely on this, and are there areas where we might need to do something more active than just rely on natural attenuation. And this involved developing a groundwater flow model, because the conclusion was that, well, given that these mineral phases are present in the saturated zone, there's no simple way to to reduce the fluoride concentrations in groundwater. Pump and treat would not reduce the concentrations for a very long time. As long as those solids are present, the solubility of fluoride is controlled, and you can't get really below that. And that's a really inefficient way. Pump and treat, for example, would be a really inefficient way to dissolve them away, to remove them. Excavation was also not considered feasible for a large part of the site just because of the depths at which some of these secondary minerals, precipitates, were present. And so we wanted to look at, well, how much can we rely on natural attenuation processes? And first we developed a groundwater flow model for the site with various types of hydrologic, geologic data, and so forth. And this is just to show you the model domain. It's fairly well defined in terms of groundwater flow because you have these boundary conditions, the river on one side, and then these ditches, which are level controlled on the other. And then, different recharge areas where there's bare ground versus paved ground and so forth. But we were able to fairly nicely calibrate a groundwater flow model for both the dry season, wet season separately. And you get these kind of patterns which largely mimic what we were able to measure. Pretty good coefficient of determination on the measured versus modeled heads, and used that as the basis for a sort of a more detailed reactive transport model for this east side of the site where the strong sources of fluoride were present, the high pHs and so forth. That model incorporated all the reactive processes that I described earlier. And it was set up in a software called FAST. It's a USGS reactive transport code that simulates groundwater flow and geochemical reactions and allowed us to incorporate all those processes. And the first step in setting up such a model is to get the right initial condition for present day. And how we did that is we did what's called a spin up to produce the spatial distribution of the fluoride associated with each of those source areas. And then that's our starting condition for predictive simulations. And then we switched to doing these long-term predictive simulations to look at effectiveness of M&A in regulating fluoride transport in the future, and also to compare effectiveness of potential remedial improvements, such as capping of the residuals areas, whether there's a long-term benefit to doing that. And here is, before I jump there, here's kind of the outline of that model domain for the reactive transport. It's smaller than the flow model domain because it takes longer to run those models. And honestly, we didn't need to have all of the entire domain set up as a reactive transport model in this case. And it's going to be flipped. It's going to be rotated 90 degrees here. So the river is down here on this image. The river is over here on the left on this image, and these are just results. So this is just kind of flip through some of the results. Initial conditions, the color coding is for fluoride concentrations in that shallow aquifer, and this is time zero, essentially present day. And as I said, the model was run up for a couple thousand years. This is after 200 years. You can see that the source areas are leaching, so the colors are getting lower down on the scale. So we have red colors here, which are in the thousands of ppm in that fluoride, the cryolite recovery area. But after a couple hundred years, they've kind of gone down to less than 1,000 and so forth, and they continue to shrink even at 1,000 years. But what you see is there's no extension of the plume towards this ditch over here. The groundwater is flowing from this area towards the ditch, but you don't see a significant plume developing. And just to show that to you a little bit differently, here's an animation of that model. So rivers on down here, and I'll run this again because it goes a little fast, and then the ditch is over here. And so groundwater is flowing from these areas towards the ditch, as well as from the riverward side of the dike towards the river. And you can see that there's a little bit of migration towards the river, but it actually peters out. The threshold blue color is at the MCL. So everything that's greater than MCL is inside that colored block. So again, this shows that there's long-term, there seems to be significant protectiveness provided by the soil chemistry in limiting where the fluoride ends up. Now I'm going to switch to talking about what happens on the other side over here, where we talked about that the ditch is very close to this closed landfill, where we expect there's significant fluoride in groundwater to this day. The landfill is capped, so it's no longer a source to groundwater, but there's a residual plume that will flush out and has been flushing out actually for several decades. And in order to improve the water quality in the ditch, we needed to consider some sort of intervention here. And what we ended up settling on was a reactive barrier that would remove fluoride. And so I'll switch to talking about that. That involved treatability studies, and then currently we're wrapping up the remedial design. And construction is scheduled to start for site-wide this year, but the PRB is probably not till next year. So our treatability study began with evaluating a kind of a wide range of potential reactive amendments for fluoride removal. And we assessed their performance based on removal efficiency, reaction rates, capacity, and as well as long-term stability. And this is kind of just showing you the types of materials we consider. There were about 15 different media. Some were mineral-based, like calcite. Some were mineral-based, but they're biogenic minerals, like bone meal or bone char. Rock phosphate, siderite are minerals again. And then a couple were just chemicals that have been either used in water treatment or considered for their high fluoride uptake capacity. And this was done through a series of tests, laboratory tests, batch tests, followed by column tests to determine capacity, and then also to determine the stability of the treatment by doing selective extractions on the column media to identify the best choice. Here's kind of an initial screening batch tests of all of those media, both alone and in some combinations to see if there was any improvement. And at the end of the day, there were 4 media that really showed the best fluoride removal. And we tested 2 different groundwaters, kind of a typical groundwater with about 80 parts per million fluoride from the west side of the site, but also because there may be higher concentrations present beneath that landfill. We also collected groundwater from that hot zone on the east side of the site with a higher pH. That would be sort of an extreme. And in general, the 4 media that performed best were the same for both groundwaters. They included these biogenic phosphates, bone meal, and bone char, activated alumina, which is a well-known fluoride treatment chemical, and hydrotalcite, which is magnesium aluminum carbonate mineral that also has been identified for its high capacity for fluoride uptake. And so we looked at kinetics as well in some of these phases to understand what the timescales would be for the treatment, because that's important in terms of designing a reactive barrier. We wanted something that'd be relatively fast. And again, those four materials that I mentioned before seem to have the best, had relatively rapid fluoride removal rates. Within about 8 days, we had reached what looked like equilibrium for most of these. And so the next step was to try to understand the capacity of these materials for fluoride uptake. We did some batch isotherm tests for all of these, including activated alumina, bone char, bone meal, hydrotalcite, and we're able to fit those to a Freundlich isotherm for each and kind of get these types of numbers. The activated alumina, bone char, and bone meal had kind of the best, the greatest absorption isotherms. I'd say the hydrotalcite was a bit lower. And given that it's also more expensive, that one was dropped from the list in terms of the ranking. As you can see here, the bone char and bone meal had slightly better isotherm constants than the activated alumina. But one of the downsides of those materials is that they tend to have, well, they have a lot of phosphate in them. They're calcium phosphates, and they tend to leach some of that phosphate out. And that was a concern for discharge to surface water, that it would impair the water body. And so at the end of the day, there were a number of these secondary water quality impacts that were evaluated. At the end of the day, activated alumina was the best choice, given all the criteria we were looking at. And here's how they kind of got ranked in terms of fluoride removal, relative costs, and water quality impacts. So activated alumina and bone char were the top two that moved forward to column testing. And there we wanted to look at the capacity of the media on an equal basis so we can evaluate cost benefit of one versus the other. As it turned out, as I mentioned, the activated, so here's the results of these column tests. The activated alumina had the longest duration to break through, slightly longer than bone char, but as expected, it was a little better. The difference in cost of the materials would have to be factored in, but that changed over time over the last couple of years as market conditions changed, specifically with regards to transport the material to the site. And I'll talk about that in a second. But to kind of counteract this issue of the bone char releasing phosphate, this shows kind of phosphate release from the bone char column versus the influent phosphate, which is this gray open circles. There is phosphate in that groundwater, but there was more when it was in contact with the bone char. When we combined the bone char, with the activated alumina, it actually removed all the phosphate from the groundwater for an extended period of time. But when we combined a little bit of activated alumina with the bone char, made a mixture, we actually could suppress that release. And so again, that's another consideration in terms of looking at what's the optimum reactive media for the reactive barrier. In terms of stability or fluoride sequestration by these treatment amendments, we saw that they were pretty good. These figures here show kind of the total mass accumulated in the column test on the media, and then how much was released either at a acidic pH, neutral pH, or basic pH. You can see that the pH has an effect on the amount that is released, and activated alumina kind of on the whole seem to do best under basic conditions. But generally, most of the alumina that was taken up was sequestered. It was not re-released under, these are fairly extreme, especially the acid and the basic are fairly extreme conditions. So we don't expect that the fluoride that's taken up in the PRB would be easily released. It should be stable there. In terms of taking these results and designing a reactive barrier, we took the column test data and fit it to a model, a geochemical model, built in Freak-C that incorporated the surface complexation reactions on the activated alumina. So as I probably didn't say that, but as a result of this, we ended up selecting activated alumina as a preferred media. It was a combination of not having these secondary water quality impacts that are associated with bone char that I mentioned, but also in terms of the availability and net cost, it was cheaper to and more effective to just build the reactive barrier with activated alumina rather than a mixture of bone char and activated alumina. And so that's where we ended up. And so in order to design the dose, we took the column test results. These are the effluent fluoride concentrations for two columns with different dosages of activated alumina. It fit to a model, so we could calibrate some of these reactions, and not so much the equilibrium constants, which come from the literature, but the capacity, the binding site density per unit mass of activated alumina. And when we did that, we also incorporated some of the information we had about during the pre-design investigations. We went and did some direct push borings and collected groundwater profiles for fluoride to see what levels of fluoride we would be encountering, the hydraulic conductivity of the soils, upgradient of where the PRBs would be, because that would be what controls the flow rate through the reactive barriers, as well as taking into account historical trends in groundwater fluoride concentrations. This little figure here is log fluoride concentration versus time over the last 30 years or so that this closed landfill here has been monitored, and it shows that over time there has been a decreasing trend as the residual groundwater plume flushes out from beneath that landfill. And so we can take that into account as well in terms of determining how long does this reactive barrier actually need to be operating based on what we know about these conditions and what we can extrapolate into the future. And so using this information with the model, we looked at the impact of different dosages of the activated alumina, and we wanted to basically, our threshold was not 4 ppm, which is the MCL, but 18 ppm. And we arrived at that number because as part of the cleanup action plan at the site, there's a screening level in surface water. If we detect levels above 1.8 milligrams per liter fluoride in surface water, that triggers some bioassays and so forth, and potentially other investigations to see what's going on. Is the reactive barrier running out of capacity for treatment, or something else going on? And so our threshold was based on that 1.8 milligrams per liter, but allowing for a dilution attenuation factor in the ditch, which receives groundwater, but also receives a lot of surface runoff. So we felt that a DAF of 10 would be applicable. And so that as long as the reactive barrier was designed to maintain concentrations coming out of it below 18 milligrams per liter, then that was an appropriate design criteria. And so you can see here the predicted fluoride concentrations as a function of these different colored curves, are a function of the actual dosage. And what it says is that anything greater than 12.5 weight percent in the PRB should be protective indefinitely. And I should point out also, there are two segments here. Based on the pre-design investigations, the areas where we had concentrations greater than 18 milligrams per liter were focused along this segment here and in this corner of the site, of that portion of the site. And so that's where the reactive barriers will be placed. And the final dosage is a little bit higher than that in order to account for safety factors and so forth. It's closer to 20%. And that was based on some extensive sensitivity analyses with the model to make sure that we would not minimize the chances for any kind of exceedance triggering additional actions in the ditch. So in summary, our treatability work and remedial design work so far identified activated aluminum bone char as effective reactive media for reactive barriers designed to remove fluoride from groundwater. And did identify that the bone char, although interesting in and of itself, it's a byproduct of meat production, beef production actually specifically. Does release some phosphate, which may be a concern depending on site conditions. And however, that could be addressed by developing a mix of activated alumina and bone char, which was one of the things we considered, but given the market conditions and the current supplies of bone char in quantities needed for reactive barrier would have to come either from Brazil or Mexico. Just the transport costs alone was what made it less appealing than just using activated alumina directly. And so that was how we ended up with the activated alumina reactive barriers. Used the model to develop the dosages that account for both future conditions as well as sensitivity analysis on variability along that length of the reactive barriers, which are several hundred feet long in total. And as I said, the EDR is currently in the final revision stage, the engineering design report, and we are hoping to be in construction within the next year or two. And with that, I will be happy to take any questions or discussions. Thank you for your attention.
Thank you very much, Dimitri, for your presentation. Excellent presentation. I mean, who wouldn't be happy if you had all the steps in there, doing the site investigation, the modeling, and the treatability study in the end?
Yeah, it just, I guess it just worked out that way. I think this was one of the first projects I worked on when I joined Anchor in 2010, and it has just progressed through those various phases. And it was always a geochemical question in terms of the groundwater treatment. And so I somehow got myself involved and have not been able to get extricated from it, let's just say.
I see that's a good thing. Does anybody have any questions for Dimitri? Because
Sure,
I
a quick
do.
question. Dimitri, so when you set up the initial reactive model, did you take into account any kinetics for fluoride, or was it more like equilibrium based?
So to calibrate the model to the laboratory experiments, kinetics did turn out to be important in order to match those curves, which you can see here. And actually, not so much for the activated alumina. For the bone char, this went through a few phases I haven't really talked about. But initially, we did this evaluation for bone char, and we did find that calcium phosphates, those reactions of going from hydroxyapatite, which is typically in bone, to fluorapatite, which is what we were making by taking up the fluoride, there is a kinetic aspect to it, and you have to correct for that because on the short time scales of lab experiments, these were over a month or two, they can be important. But when we then upscaled it to do the field design, the groundwater flow or groundwater residence times within the PRB were on the order of many months, and so the kinetics were not so important. It sped up the execution of the model to just ignore them at the end. We did do evaluate to what extent that would affect the results, and it was not significant. So it really depends on what you're trying to model. You might, to get the right parameters for a field scale model from lab studies, you might need to do something a little more detailed and accounting for kinetics and things like that. But in this particular case, the upscaled model turned out could be done much more simply once we had the calibration.
Very cool. Thanks. Some great thoughts there.
Indeed. Anybody else have a question for Dimitri?
Hi, Dimitri. Thank you for a great presentation. It was really interesting. I eh, I'm a PE, but I don't do anything like this, so it was fascinating to me. But I'm just wondering, since we have a little bit of time, and if nobody else has any important questions, the slide that had the cartoon on it, as you called it, I was wondering if you could go back to that
Sure.
and
Let's
just show it. Just you went by it really quick, and so I didn't really get to take a look at it. If you could just maybe give me like a quick summary on it.
Absolutely, yeah. And
Thanks.
it's because I was oh, let me get rid of this thing here. Okay, it's because I was repeating basically what was on this cartoon. So a little ahead of myself. So this is where some of these residual materials would be landfilled, for example, on the site. And there may be an existing cover, or that would be part of the remedy, is to cover up uncovered materials. But it starts with precipitation on these materials that contain residual fluoride, and we had characterized it in the form of a calcium fluoride material, mineral phase. And we had leaching data from lysimeters, so we could characterize the source term that goes into the groundwater. And once it gets into groundwater, the fluoride is transported along groundwater flow paths, and it comes into contact with these soils that have exchangeable or reactive calcium, either in the form of like exchangeable calcium in clays or calcium that's associated with some of the soil minerals, like feldspars, which are quite abundant. Uh, and that drives a reaction where, this material here is also rich in sodium, as I mentioned. That drives a reaction where the sodium pushes the calcium out of the solid phases, the exchangeable calcium out of the solid phases and into the groundwater, where then it reacts with fluoride to precipitate those nice calcium fluoride crystals that I showed you. And so that has really limited the lateral movement of fluoride. So you don't really have long plumes developing down gradient of these deposits. But what you have in exchange, though, is that you have secondary fluoride sources in the saturated zone. And so they continue to maintain, if you were trying to clean up groundwater by putting a well in here and pumping it, you'd be pumping water that would always be going into equilibrium with that mineral phase. And so, you wouldn't clean up the groundwater. You wouldn't restore the aquifer in any reasonable time frame because fluoride is sparingly soluble. It's not easy to dissolve it all the way. It would take, hundreds or thousands of years. And so you're really stuck with managing the stuff in place. And this seems to be a recurring theme at smelter sites where they were operated for some decades, and you have these secondary fluoride sources below the water table that make it very difficult to do anything that would quickly clean up the groundwater. And so you're looking at, essentially protecting groundwater discharge, this pathway, the groundwater discharge to surface water, making sure that if the concentrations are above what's acceptable for surface water, then you might need to put something here to intercept that, like a reactive barrier is a passive method. You could put a trench in and just pump that water out. That's probably, similar to having a pump and treat system that would have to run forever or something like that. But understanding just how much capacity there is, how much calcium there is for fluoride that is leaching through here. And, once you cover it, the amount of fluoride that's leaching kind of becomes de minimis. There's no addition. It's just whatever's already down here. But whatever's down here is either already taken up in the soil, or if it moves forward, it reacts with soil that it hasn't reacted with yet, and it gets taken up. So the advance of that secondary source of fluoride is extremely slow compared to groundwater flow conditions. So it's like a super high retardation factor if you think of in kind of more traditional groundwater transport terms. But oftentimes you think of fluoride, it's an ion. It probably just moves around with water. It in some cases it can, but in this particular setting, because of the chemistry of the soils, it can't. Yeah. So
Thank
that's
you.
kind of yeah.
Thank you.
So
I
would you
have a
consider
question.
this? Sorry. Go ahead, Giovanni. Yes.
Sorry, I just jumped in. Thank you for the presentation. I had
Sure.
a question on if you found or if you consider any competitor for adsorption or exchange with aluminum, activated aluminum. Like, for example, other metals or ions in groundwater that could
Oh,
compete.
yeah. Well, actually, I showed you one, which was the phosphate that was present in the groundwater because it was leached by those high pH solutions that infiltrated into the soils, was removed by aluminum. And so that was also something we wanted to make sure that, I'm sure it affects the capacity for fluoride because both both phosphate and fluoride are anions, and so they probably bind to similar sites on the activated alumina. But we used site groundwater, so whatever was in the groundwater was already taken into account.
I see. Thanks.
Anybody else have a question before I go ahead with mine?
Yeah, I had a question. Is this reactive barrier expected to last in perpetuity? And if not, what are the ways to replace it or replenish it in the future?
So that is a key question in terms of getting a design approved. And so in terms of our modeling, it was designed for the media to last forever because the source term, as I mentioned, that residual groundwater plume beneath the closed landfill is flushing out. The concentrations reaching the edge of that landfill have been decreasing over time exponentially, and we can project what that might be. And so that would be like a nominal design. It would be based to, it would have to operate for as long as those concentrations are expected to exceed the threshold that we use, the 18 milligrams per liter. So we can calculate that time frame, and the dose that's in the PRB has to, at the first level, take that into account. There's also lateral variability in those concentrations and groundwater velocities along that ditch alignment. And so there's variability that we also need to take into account, and we did do that in a sort of probabilistic way. That was part of the sensitivity analysis. And then there's always the fact that a model is a model. You do your best to design something, but you still have to have some kind of fail-safes, right? And so there's some safety factors. There's a long-term monitoring plan where we would have to identify if there's an exceedance in the ditch or a persistent exceedance of the surface water level in the ditch, then that triggers other investigations to understand, is it really because the PRB is starting to be spent and we need to, or is there something else? There's soils downgrading in the PRB that would have to flush out first before we start to see the effect of them. There's other potential sources. Maybe there's, erosion from unknown areas that there's some residuals that haven't been mapped out. So all of these things are worked into the compliance monitoring and contingency response plan that's being developed for this project. So there are a number of steps, and there's a whole decision tree on, okay, if we find this, what do we do? And so there are a number of triggered actions. And the final one is if everything points to that the PRB or some section of the PRB is not working, because we wouldn't assume that the whole PRB starts to fail. It would be probably sections where you have higher mass flux, where you're reaching the capacity faster than other sections. Then we could go in and replace that portion of the PRB. Probably by the time we look at that, there may be options to actually regenerate the chemistry by some kind of, and this is just me thinking about it now, but this is probably what I would be thinking about down the road, to develop an approach where you can inject chemicals to remove the fluoride, pump it out, because there it'll be easier to pump out. It's mostly sorbed on the activated alumina, and then in doing so, regenerate the surfaces so they have capacity again. So I think there are options. I think that, and in order to get regulatory approval for something like this, there are a lot of those kinds of steps that have to be incorporated in the long-term monitoring plan.
Thank you.
Yeah.
Excellent. I wanted to ask two questions, but I'm going to ask only one because we're almost over with time. And I don't pretend to be a geochemist, but why was the pH high that you mentioned at the beginning, that in that portion of the, where you had the fluoride mass, there was high pH. What was the reason for that?
So when they took those carbon pots, the pot liners, which is what they collected the aluminum in, the molten aluminum, they also had all these salts, all this cryolite that had precipitated inside the carbon pots. So they take them, they would crush them, and they would leach them with sodium hydroxide to dissolve the fluoride. And so you ended up with this is, in the 50s, 40s, 50s, 60s, et cetera, you ended up with solutions. So, and then they placed that material out on the ground after they were done. So it had some residual solutions in it, moisture, high pH, high fluoride stuff. They would just get as much as they could out. And so that's what leached into the ground. And so it was a high pH sodium fluoride kind of solution that was a residue on those crushed carbon materials. And and so if it hadn't been sodium, this might not have worked, because the sodium is what pushes the calcium out of the clays into the groundwater so that it can react with fluoride.
Binds the fluoride,
Yeah.
Super cool.
Thank you.
We are right at the top of the hour. Thanks again, Dimitri, for the excellent presentation, and thank you everybody for attending today. And I think we're gonna have Caitlin, I think, another presentation next month, from what I saw. So stay tuned, and see you all virtually next month.
Thank you. It's been a pleasure.
The pleasure was ours, Dimitri.
Thank you. Bye.
Take care. Take care, guys.